So in these examples, we're going to see how to use the method of watchwork to calculate the displacement in our truss structures. So here we have a four-member truss A, B, C, D. There's external load 5 kN applied vertically on the joint A, and we want to know the vertical displacement of joint A. So we know for truss structures, the equation for the method of watchwork can be written down like this. We have 1, so is unit load times dirt. So we want to know the vertical displacement. So we show delta A, y is a vertical direction, and equal to summation. We have 4 members, I equal to 1, go to 4. So the small ni and capital Ni, L, and Ea. So this is the equation of the method of watchwork for truss structures. So look at these terms. We have Ni, small ni, this is for the virtual member force. And the capital Ni is a real member force, and L is the length or dimension of the member. E is the Young's modulus, A is the area of the members. So we need to know all these items in these terms. So first of all, we need to know the dimension, okay, L. So we can put dimension on the structures. So here we have, so see here we have 2 meters, and BC is 1.5 meters. So then this is a right triangle, so we can know, we can easily write down that BD is equal to 2.5 meters. And also AB is 2.5 meters. So this is dimension of BC is 1.5 meters. So this is dimension of truss members. So AD is 3 meters. Once we know the L, we need to know the capital NA, the member force of the truss. So first of all, let's to calculate the member force in the truss. We can either use method of joint or method of section to calculate the member force. So first of all, we put the reaction force on the truss. So on the support C is a pin support. We know the reaction force is Cx. On the vertical direction, reaction force Cy. So we have R dx, R dy. So this is 4 reaction force on these truss structures. Then we can use in the equation of equilibrium to come out the value of some of the reaction force. So first of all, we can see if we write down the moment equation of equilibrium at node joint D, we can solve RCX because Rdy, RdX, RCy, they don't have a moment on joint D. So first of all, we write down equation of equilibrium at joint D. So equal to 0, we assume the clockwise direction is positive for this equation. So we can write down first of all is 5 kN have a moment go to counterclockwise, so it's negative. So it's negative 5 kN times the lever arm is 3 meters. Okay, so this is a moment due to this 5 kN. We know RCX also have a moment at D and go to counterclockwise, so it's negative as well. So RCX times the lever arm is 2 meters times 2 meters equal to 0. So then we can calculate RCX is equal to negative 7.5 kN. So the negative sign showing here, that means the initial assumption of the direction of RCX go to left is not correct. So the direction must go to right. So we just leave it like this, and we will correct it later. So this is RCX. And then we can calculate Rdx as well, because we can easily write down the equation of equilibrium in x direction equal to 0. So if we see go to right direction is positive, so we have negative RCX and negative Rdx equal to 0. Then Rdx is equal to negative RCX is equal to 7.5 kilonewton. It's positive, so that means RDX is go to left direction, so this way. So then let's look at the joint C. So look at joint C, we're using method of joint to come out the member force and reaction force. So number of joints. So look at joint C. So we have joint C. This is joint C. We have RCX. We assume the member force FBC is number BC is in tension, so it's go outwards from the joint C, and we have RCY. Okay, so in this direction. So look at this free body diagram of joint C. We can easily find out that based on the Fy equals 0, so we can find RCY equals 0. There's only one force in y direction, RCY equals 0. So on Fx equals 0, in this equation of equilibrium, we assume the positive direction go to right. So we have negative FBC, negative RCX equal to 0. And then we know FBC is equal to negative RCX. So we know RCX is negative 7.5 kilonewton. So here is 7.5 kilonewton. So this is FBC. So now I want to put the force FBC over here. So it's 7.5 kilonewton over here. So this is member force in BC. Now I would like to look at the joint A. Okay, I want to use a method of joint at joint A to calculate the member force in AB and the member force in AD. So let's look at how to do it. So we draw the joint A. Okay, this is joint A. We know there is a 5 kilonewton force on joint A, and we have member force FAB and member force FAD. So we assume FAB, FAD are tensile force. So the direction we draw that. So here this is FAB, this is FAD. Okay. So to solve this, we must know the angle of this one. So we call this theta. So we can find that for this. So for this angle theta, we can find the sine theta. So sine theta is if we see there's a triangle over here. So this triangle over here. So for sine theta is the length of this one over the length of AB. So this is 2 meters. AB is 2.5 meters. So sine theta is 2 meters over 2.5, then that is 4 over 5. We can also calculate cosine theta is equal to, so the length of this one is 1.5 meters over length of AB, 2.5, that is 1.5 to over 2.5, that is 3 over 5. So once we know the theta, so we can calculate FAB and FAD. So we know here's theta. So first of all, in y direction, y equal to 0, so positive is go up. So we have FAB sine theta. So FAB sine theta. So this is FAB sine theta. FAB sine theta go upwards, like minus 5 kilonewton, go downwards, so equal to 0. Then FAB is equal to 5 over sine theta. So sine theta is 4 over 5. Then this is equal to 25 over 4. That is, so we can get FAB is 6.25 kilonewton. So the direction is positive, so that means FAB is a tensile force. So this is FAB, and in x direction, we can write down like this. So we know FAB. So we use this one. So FAB have a component. So this is FAB cosine theta. So FAB cosine theta plus FAD equal to 0. So then we can calculate FAD equal to negative FAB cosine theta equal to 6.25 kilonewton times 5/3/5. Though from this we can calculate the result is using calculate. We have 3.75 kilonewton. Okay, this is member force AD. So we got, so look at what we got. So let's move this. So we got BC is 7.5 kilonewton. We calculate FAB. FAB is showing here, so is 6.25 kilonewton is a positive value, and FAD is negative 3.75 kilonewton. So we put the value over here, so that is 6.25 kilonewton, and AD is negative 3.75 kilonewton. And the only one member force we don't know is member BD. Okay, so member BD, so we can draw the joint B. So let's see how to do that. So if we draw the free body diagram of joint B, so this is joint B, and at joint B we have 3 members: BC, BA, and BD. Okay, so BC, FBC, FBA, and FBD. Okay, so for this one, if we see the angle here is beta. Okay, so we can find in vertical direction FBA. So this is beta, so we can also derive that this angle is also beta as well. So based on the geometry relationship, so we can see the FBA times sine beta plus FBD times sine beta equal to 0. We can easily find FBD is equal to negative FBA. So FBA we're showing here is 6.25 kilonewton. So it's negative 6.25 kilonewton. So this is FBD. So FBD is a negative value. So we put the value here. So it's negative 6.25 kilonewton. So this is 4 member force. So once we got a member force, then we can, so we got this value, then we need to know the virtual system, the member force of a virtual system, small n and I. And before we go to the next step, so let me show you how to determine the remaining reaction force. We know RCX is equal to negative 7.5 kilonewton. So the direction is this way is not correct, so we can put the direction like this. So this way, so is 7.5 kilonewton. So this is RCX. RDX is 7.5 kilonewton as well. And then we know RCY equal to 0. Okay, so if we write down the equation of equilibrium in y direction for the whole systems, so for the whole systems, we can see for these whole systems, we know 5 kilonewton going downwards, so it's negative, and RDY plus RDY equal to 0, then we can derive dy equal to 5 kilonewton. So dy here is equal to 5 kilonewton. So we continue on this. So let's put 5 kilonewton over here. So even probably in our example of method of virtual work, we probably don't use this reaction force, but I just want to show you how to got all the unknown force in these structures. So in next video, I'm going to show you how to finish this question by using method of virtual work. I will see you later.